Hi, welcome on my talk on improving address-based inference for SYCL program. I'm Victor Miller. I'm a research engineer at Quickly. Since 2015, I spent most of my time on Compute CPP or SYCL implementations, where I've been the co-owner of its compiler, and I'm a contributor to the SYCL specifications. Today I'm presenting the work that has been done with Ross and others here at Quickly. This is a niche talk that talks about very specific points of address-based management done during the device completion of SYCL programs. We'll cover some basic points about address spaces, address space inference in SYCL 1.2.1 in 2020, and move on to our new approach and get some conclusions on points to consider for well-formed extension. So SYCL is an open standard maintained by Kronos to provide a single source C++ based programming. Various implementers are implementing the SYCL, and combined implementations provide support for various backends, such as OpenCL 1.2 to 3.0, CUDA, heap, level 0, etc. Right. So this is a very simple example of a SYCL program. The main point to take here is just that the kernel that is executed on the specific device is marked as a function that is being passed to the parallel4 function. To compile such program, most of SYCL implementations use the split compilation mode, where you have the device phase that takes the source files and only processes the function that are reachable from a parallel4, and the result is some intermediate representations like POV or native ASA like AMD-DCN. And the host compilation phase is just a simple regular C++ compilation process. You combine the two results of the two phases in some implementation-defined way, and pass it on to the linker, which formed the final application. The main model employed by SYCL is based on the OpenCL1, and it's critically important for the device compiler to take that into account to yield the best performing code. So roughly, there are a generic hierarchy of memory that each of this memory can be reached by different computing elements. We have the private that can only be reached by one computing element, local that is shared by a certain group of computing elements, and then the global memory that is shared by all the computing elements. There is also a constant memory, but SYCL no longer exposes this one, so we're going to ignore it during this talk. Address spaces are used inside the programs to actually tell which memory is being accessed. Nowadays, most programming models offer a generic address space which overlaps the different address spaces in order to ease the programming. SYCL do support generic in 2020, but only if the backend supports this. If it doesn't, then the infer mode has to be used in order to remove all the usage of what would be generic pointers. So what do we want inference when we can use most of the times generic address space? The support of generic is widespread on many platforms and including embedded ones. However, there's still reasons we want to use an infer mode with SYCL. The usage of generics can induce a runtime cost. So that's something you might want to guarantee that you can alleviate. But the main motivation here is simply just the backend support. SYCL doesn't have a specific offloading API that you must use. And you may want to run on top of OpenCL 1.2, which doesn't define generic at all, so the driver JIT isn't likely to support that. And OpenCL 3.0 have a generic support, but is optional, so a driver might not support that. Vulkan is also a potential target for SYCL, and there is some experimental support for this. But this POV flavor that is being used does not allow for the generic address space we use. So now we covered the basics very quick, very briefly. Let's have a look at the inference mode. So the first step here is the core web application. So it works really in tandem with the address space inference. This ensures that inference will not stop at the function boundary. So if we look at the code sample here, we have a function foo that takes a pointer to some undeduced address space. Later, we have two calls to foo. One was called with a pointer that we deduce to be to global, and one is to a pointer that we deduce to be a to local. If we simply try to infer address space for the function foo, we have a typing issue because we have two calls with two different types. So in order to solve this without using the generic address space, simple things we can do is actually just to duplicate or clone the functions to create the variant we need when they are being used. So here we duplicate the function foo to generate two variants, one that takes a pointer to global and one that takes a pointer to local. And we'll update the body of the functions during the duplications. Once we created that, we redirect the call to the aggregate, overload the foo, and that's the duplication process. So of course, we can't generate all the variants of each function speculatively, as generating all the variants would be way too expensive, and some variant could actually generate illegal code. The instant variants are only created because we are actually calling the function. So the process is applied recursively. So let's say we provide a body to our foo functions, which just called another function bar. Then we also duplicate the function bar for the appropriate address spaces. So one that takes a global and one that takes a local. So in the end, we end up with a program where we derive twice the function foo and twice the function bar. Now, the current inference rule in SYCL 1.1.1 in 2020 is more of a deduction process rather than true inference. It deploys a greedy approach where pointers and reference types are deduced when they are declared. So for variables, the type is deduced using the initializer. For function parameters, this type update is performed using the argument type that is passed to the functions, as we saw just before. And that triggers the duplication process as well. So in the first example that we have here, piece type is updated to be a pointer to global because we have an accessor to a buffer, and that normally points to a global address space. So we can do that to update. If there's no initializer, the types will default to private. So in the second example, we move the initializer into a second statement. So now P doesn't have an initializer, so it has to default to private, and that's causing a typing error here. To work around some deduction issues, the user may use the multi-pointer class as well, but that's really for local working around. So the current rules allow for large and significant applications to develop. We ported IGN and TensorFlow onto SYCL under the rules, and it just works fine. However, the proper introductions of generic address space and introductions of the USM feature in SYCL 2020 made the current rules very, very limited. The main limitations really derive from this greedy approach and this defaulting mode that we have. On top of everything, there is still ambiguities in 1.2.1 and 2020s, and it doesn't cover all the aspects of C++ language that it should. So we really need some kind of an update anyway. To emphasize a little bit more on why USM feature is actually a problem, if we take the example that was shown earlier, but express the lambda as a simple struct kernels, we can see the buffer fields of the kernel that represents a USM pointer. Because it is unconstrained, that field has to default to private. However, USM maps to the global address space. So we can't place the buffer that we are passing actually through the parallel for onto that kernels in the device. That creates a typing issue for the compiler. So the only way for the user to work around this problem is to use a multi-pointer class or a wrapper class that would actually incorporate that global address space directly in there. But that can only lead to a large discrepancy between how one would use this feature. If it can support generic, it would just write a row pointer, or using the inference mode using a wrapper class. That's one of the main motivations for making that update. So the new approach, the basic idea is put fewer constraints on the user at the expense of complexifying the implementation. So what we want is just to maintain a good support for new SYCL features like USM on platform not supporting generics, and encompass more program that is being written with generic in mind. So the idea is really to have a compiler that can handle a strict subset of legal programs when the generic used is being used. That is, if a program is compiled with an inferred address space, then it will compile using generic pointers. But the opposite might not be totally true. In other words, we're not trying to make every single program written with generic pointers in mind, compiling in infer mode, but handle a really reasonable set that can handle all the modern features of SYCL. So the compiler is moving away from the simple deduction mode we described before, and employs more traditional type inference techniques. Instead of greatly deduce address space and default to private, the compiler will actually apply constraints to the different variables and types and unifying them for each function. It will ignore to some extent the default to private rule in order to allow the algorithm to get more room to infer types. We also extend the procedures to structures, and we can also duplicate them in order to define different variants of the same structure to have pointers to different address spaces in order to cope better in the different way they can be used inside a program. So a few running examples to show the basic idea that is behind. So when a user writes to functions, the compiler will take that as some kind of templated function where the template is just some symbolic address spaces that we apply for each of the pointers. So for instance, this function foo takes 2 pointers and returns 1. So we add symbolic address spaces to these pointers, A, B, and C, that annotate that into some kind of pseudo C++ template notation. So that's what it is. We do the same for structures. So for instance, if I have a structure data, I'm applying symbolic address spaces onto that data structures, and for function that actually uses that structure, I'm applying different sets of symbolic address spaces, so each of them can have its own derivations to specific address spaces. Now, what we want mostly with this is actually first unify and trying to find relationships inside the interface of each function. So if you provide a body of the foo functions in our initial example, the definition is made of a simple ternary expression. The value stored is A, it's even, you return to pointer A, otherwise return to pointer B. In this case, we get a very simple process. The return expression is asserting that C must be equals to the type of our conditional expression, and the conditional expression is telling us that the address space A and B must be equal. So if we follow on with simple unification process, we end up with A that must be equal to B and A that must be equals to C. So therefore, we can simplify these expressions by just using one symbolic address space. This A, and everything has to be using the same address space. We don't know anything about which address space to use, but we know how they relate to each other. So now, if we are writing a function bar that actually calls foo, so it's taking a pointer that takes some symbolic address space A and a pointer that we fixed to a pointer to global. As first step inside the body of these functions, we assign to a symbolic address space T to a variable T. And we can move on that to every variable that exists inside the functions. And once every pointer variables has a symbolic address space, we can move on to unification. Second statement inside this bar function tells us that the address space T and A must be equals because of the return type of foo. And the parameter B that we pass to foo is actually setting A to be equals to global. So we can now simplify this whole function to remove the address space, symbolic address space A, because it has to be global, and simplify the whole functions to use the global functions, the global address space. Right. Now, another part is we must be able to raise error when we have typing issues, and typing issues mean we need to use the generic address space. So here's an example that we need to raise an error at the call site. So if we look at the function error, it tries to pass to foo 2 pointers to 2 distinct address spaces, one to local and one to global. Due to unification process before, we know that type A and B has to be equal. So this means that we need here a generic address space in order to compile these functions. We need to convert A into the generic address space and B into the generic address space for this function to actually be to compile. So now under these new rules here, we have to raise an error there. In the current specification that we have, we would also have to raise an error, but that errors would normally have been raised during the duplication process of foo, because we pass on 2 pointers and then we're trying to rebuild the body of foo, and the conditional expressions is telling us that A and B actually must match. So we'll stop here, as there's not much more to explain on to give you the idea of the unification process and how we deduce the address space. Instead, we're going to discuss a little bit more, a few points that we need to consider in order to keep all programs well typed. So we glossed over how to express general case. However, there's a few points that we need to consider in order to ensure that generated programs are being kept legal. The first is their consequence of our premise, dropping the default to a private rule. If a variable or field isn't getting constrained or doesn't unify to a concrete address space, defaulting private is no longer the best options and can actually be dangerous. So here the simple kernels, although quite tricky, that takes 2 USM pointers in and out, and each of these pointers is actually a pointer to some int. So the 2020 specification tells us that in and out actually have to be pointers to the global address space because they are USM pointers. So just by looking at the current rules, we already know the first level has to be a pointer to global. So it's a pointer to global to some undeduced address space. Now, if we start to, if we default A and B to private because the body of the function doesn't tell us which address space to use, this would actually be a problem because we just got a pointer and we're not initializing this. So a pointer to private would actually be a pointer to some undefined memory. So there is no other possibility for legal programs that would use such pattern to actually be for A and B to be too global, because otherwise any other pointers would actually be completely undefined. So in that case, a more smart solution to our problems is actually having a pointer to global that is a pointer also to global. There's still cases that we need to clarify, but clearly private here is no longer a straightforward options and actually give you a problem in that kind of cases. The biggest problem now that we have as well is handling cast. It's a must for any C++ programming model. And of course, it's quite tricky when we have a type inference system that has to deal with a type evasion system. So there is cases that we need to reject because they start to be dangerous, and there are others that can be safely used if we follow proper rules. So for instance, the reinterpret cast that we have at the top here, we simply reinterpret the on-aligning type that is being pointed to. Because we're operating in a mode where generic doesn't exist and you can't change one address space into another legally, it means that you can actually pass on the address space through the casting and interpret the cast that we have here. Second case can be a little bit more controversial. So we have two structures, foo1 and foo2, that each takes a pointer to some types. So they have a similar layouts. And in our example below, we actually reinterpret the pointer to foo1 into a pointer to foo2. And in that case, we might want to pass on the address space onto the first level. That's true. But also within the field F, because here the only thing that we're actually doing is just reinterpreting the type. So there's no reason that why you would also want to change the address space underneath. However, how to exactly articulate that kind of cases and whether this is actually a good idea to allow this is still under scrutiny. So we're just trying to find out the corner cases there. One case that we must actually reject is pointer to integer and integer to pointer cast. It's actually a problem here. We could do some kind of analysis that would track the provenance and keep track of the address space throughout the different programs or different just the function. But that would raise the complexity and the cost of compiling such functions. So it's probably not something that we would want to get into any compiler. Another point relating to cast is that we need to stop the propagation of the cast analysis through function boundaries. So let's assume that the user wrote a memcopy function and takes in void pointers. Then it's calling, then in calling functions, he just initialized a structure using another one. Then we might want to actually move on the information that we hold about address spaces from T2 to T1. However, this is not really doable in practice because it also implies interprocedural analysis. Here is just one level of functions, but that can be deeply nested, and that would start to complexify and increase the cost of compilations quite heavily. So in the cases, we're actually orienting ourselves to limits to an interprocedural inference, so we don't end up in too high cost. However, the memcopy case, for instance, is actually quite important, and while the general case should be banned, like user writing and so on, looking into spatial casing some of the standard library functions is actually an option that we are looking at. So we know by the C++ specs that what memcopy does, so we can embed that knowledge inside the compiler, and that would be kind of safe and actually a useful thing to do. That may look strange, but this is already actually happening in SYCL 2020 and some other programming models. So it is part of the core C++ specifications, just like the language part. It's just not a de facto library that is being written by someone. So we know its semantics, and we can take advantage of it to carry more information. Also taking advantage of some idiomatic programmings, meaning that the user is actually likely to use his functions rather than writing his own, because best practices encourage this. So that means overall have way better integrations into the C++ ecosystem, and is not that expensive to do. So here we go. We have presented our prototype compiler and how it works. A new approach allows for more rich programs to be written while guaranteeing that no generic pointers will be used. New rules are more complex to express, that's true, but it remains simpler to what you would find with some other general purpose language like SYCL, for instance. The main complexity is being to explain the constraining approach, but that's nothing new in the typing world. And the other part is to handling cast, and that would be a bit tricky, but it's not something that is not doable. The result is we can support more modern SYCL features and more elegantly, and especially the USM feature. So currently the work is still ongoing, and we are trying to bring the prototype compiler into a production ready state. You can already try it out, but the experience may vary in some places. The main area of focus will be to improve the error reporting to users and the general performance of the compiler. And of course, following this, we also need to articulate a proper specification document. Thank you very much for watching the talk, and I hope it was very insightful for you.